Hi, I'm XIAO from Group 4 in Section 4. I will be demonstrating the circuit design and waveform simulation results in Quartus Prime software. To design the arithmetic logic unit, I will start with constructing a 1-bit full adder. The circuit will have 3 inputs and 2 outputs with 2 XOR gate, 3 AND gate, and 1 OR gate. Now, let us run the waveform simulation. Okay, so 0 errors. Now, file, new, university program WF. Okay. At here, I will put random values at fixed 100 nanosecond intervals. All the input is also the same. Before we start the simulation, we need to delete the no read out. Now let's run the function simulation. During 0 to 1 nanosecond, A is equal to 1, B is equal to 0, and C is equal to 0. Therefore, S, the sum is equal to 1, and C out is equal to 0, which shows that the design of 1-bit full adder is correct. Next, we save this 1-bit full adder as a symbol and use it to create the 4-bit full adder and subtractor. The circuit will have 2 4-bit inputs, 1 1-bit input, and 1 4-bit output with 4 symbol of 1-bit full adder and 4 XOR gate. Note that the 4-bit inputs and output is connected using bus, and the C out is ignored according to the design step. Now, let's run the waveform simulation. No errors. File, new, university program WF. Okay. Now I will put random values at fixed 100 nanosecond intervals. And I will delete the no read out in the simulation settings. Run function simulation. During 0 to 1 nanosecond interval, ALUOP is equal to 1, which means addition will be performed, and which gives us a result of 4. And during 100 nanosecond to 200 nanoseconds, ALUOP is equal to 0, which means subtraction will be performed, and this will give us a 10, which shows that the design of 4-bit full adder and subtractor is correct. Now let's move on to the next part. We will design a 1-bit 4-to-1 multiplexer. The circuit will have 6 inputs and 1 output with 2 NOT gates, 4 AND gates, and a OR gate. Now let's run the waveform simulation. 0 errors. New. Music program WF. Okay. I will put random values at a fixed 100 nanosecond interval. Remember to delete the no read out in the simulation settings. Run function simulation. During 0 to 100 nanosecond, the selector lines S1, S0 is 0. Therefore, output is equal to I0, which is 0. This shows that the 1-bit 4-to-1 multiplexer design is correct. Now, we will save this 1-bit 4-to-1 marks as a symbol and use it to create the 4-bit 4-to-1 marks for A. The circuit will have 4 4-bit inputs, 1 2-bit input, and 1 4-bit output, and connected by using 4 symbol of 1-bit multiplexer and bus wiring. Now, let's run the waveform simulation. 0 errors. File, new, university program WF. No pointer, this. And here I will put a random value at a fixed 100 nanosecond interval. Before we run the simulation, we need to delete the no read out in the simulation settings. During 0 to 100 nanoseconds, A cell is 1. Therefore, A1 will be selected as the output of A, which is 7. This shows that the design for 4-bit 4-to-1 multiplexer for A is correct. We will also use the 1-bit 4-to-1 multiplexer symbol to create the 4-bit 4-to-1 multiplexer for B. The circuit will have 4 4-bit inputs, 1 2-bit input, and 1 4-bit output, and connected by using 4 symbol of 1-bit multiplexer and bus wiring. Now let's run the waveform simulation. And here I will put random values at a fixed 100 nanosecond interval for all the inputs. Before we run the function simulation, we need to delete the no read out in the simulation settings. Run function simulation. During 0 to 100 nanoseconds, B cell is equal to 3, which means B3 will be selected as the output of B, which is 12, 1100. This shows that the design of 4-bit 4-to-1 marks for B is correct. Now, the last component in the arithmetic logic unit design, 4-bit D flip-flop is created using 4 1-bit D flip-flop, and the circuit will have 1 4-bit input, 2 1-bit inputs, and 1 4-bit output. They have a common clock signal and reset signal, and the inputs and outputs of the 4 D flip-flop is connected using the bus wiring. Now let us run the waveform simulation. Zero errors. And here I will put random values at a fixed 100 nanosecond interval. Remember to delete the no in the function in the simulation settings. So during the 200 to 300 nanosecond interval, reset is equal to 1 and there is a positive edge of a clock. Therefore, the Q out is equal to D in. This shows that the design of 4-bit D flip-flop is correct. Now we will save this 4-bit DFF as a symbol and use it to design this top bridge. It has the same function as the 4-bit DFF, only the output is changed to ALU out. Now all of the components for the ALU has been done. So we will save this 4-bit full adder and subtractor as a symbol, 4-bit 4 to 1 multiplexer for A as a symbol, and 4-bit 4 to 1 multiplexer for B as a symbol, and the last one, this top bridge as a symbol. So now the multiplexer for A and the multiplexer for B is connected to this 4-bit full adder and subtractor using the orthogonal bus 2. Then the 4-bit full adder and subtractor is connected to the DFF also using orthogonal bus 2. A0, A1, A2, and A3, which are 4 bits each, and B0, B1, B2, and B3 are also 4 bits each, and they are both connected to inputs using orthogonal bus 2. The ASEL and BSEL are 2 bits each, and they are also connected using orthogonal bus 2. The ALUOP, clock and reset are only 1 bits each, and the output ALU out is 4 bits, and we completed the design for our arithmetic logic unit. Now let's run the waveform simulation. Zero errors. And here I will put random values at a fixed 100 interval for all inputs. It didn't in the simulation settings. So during 0 to 200 nanosecond interval, because the reset is zeros, therefore the ALU out is 0. So during 200 nanosecond to 300 nanosecond interval, the reset is 1, which means there will be an output. So there is actually a delay here, so we should look at here. And A cell is 1, which means A1 will be selected, which is 8. And B cell is 3, which means B3 will be selected, which is 0. And ALUOP is 0, which means subtraction will be performed. So 8 minus 0 will equals to 8. And then it will maintain. And when the reset is 0, the ALU out will be 0 again. And when the reset becomes 1, but there is no positive edge of the clock, so it will still maintain until here. And then at here, the A cell is 2, which means A2 will be selected, which is 1, 1, 0, 0. And B cell is 1, which means 0, 1, 1, 1 will be selected. And then there is actually delay here, so ALUOP is 1, which means addition will be performed. And the reset is 1 at positive edge of the clock. Therefore, the output is 0, 0, 1, 1. This shows that the design of our arithmetic logic unit is correct. And that's it.